Today, we are going to understand another topic of flow through pipes, which is flow through parallel pipes. Here also, we'll be deriving the equation for the length of equivalent pipe as we had derived in the case of flow through pipes in series. First of all, let's just understand when do we use parallel pipes. Like here, as you can see, I'm having this single pipe and it is carrying a discharge of 50 मीटर क्यूब पर सेकेंड. अब मुझे डिस्चार्ज इंक्रीज़ करना है एंड आई वांट टू मेक इट एज 150 मीटर क्यूब पर सेकेंड. मतलब ये जो मेरी पाइप है इट शुड कैरी अ डिस्चार्ज ऑफ 150 मीटर क्यूब पर सेकेंड. फॉर दिस व्हाट आई एम डूइंग इज़ मैं ऐसे पैरेलल पाइप्स लेके अपना डिस्चार्ज इंक्रीज़ करूँगी. Like this is my main pipe. Then I have divided it into two or more branches. As here you can see we are having 3 branches. This and this. These we call it as branched pipes. तो मैंने मेन पाइप अपनी ली, उसे 3 ब्रांचेस में यहाँ पे डिवाइड कर दिया है. These are my branch pipes. And then again this is becoming a single pipe. ये जो ब्रांच पाइप्स है मेरी वो पैरेलल में कनेक्टेड है. दैट्स वाई वी कॉल इट एज फ्लो थ्रू पैरेलल पाइप्स. एंड वन मोर एडवांटेज वी गॉट बाय कनेक्टिंग द पाइप्स इन पैरेलल इज़ वी हैव इंक्रीज्ड द डिस्चार्ज. तो जो डिस्चार्ज मुझे कैरी करना था वो अब आई कैन कैरी दैट बाय pipes in parallel. Now suppose the discharge in the first branch pipe is say Q1, then in the second branch pipe it is Q2 and in the third branch pipe it is Q3. तो यहाँ पे जो total discharge होगा that will be the sum of this Q1, Q2 and Q3. That is, I can write here that the rate of flow or the discharge Q will be equal to the summation of these three, which is Q1 plus Q2 plus Q3. Then talking about the head loss, तो तीनों ही जो ब्रांच पाइप्स है उसमें हेड लॉस सेम रहेगा. So we can write it here that head loss for each branch pipe is the same. Like for the first branch pipe, the head loss, say it is HF1, for the second one HF2, and for the third one HF3, and all of these three are equal to H. Now we already know the Darcy-Weisbach equation. We'll be applying that here. Firstly, let's use the continuity equation, which is Q is equal to area into velocity. Area is pi by 4 d square into V. Here I'm saying that the diameter of the branch pipes are d1, d2 and d3, and the velocity is v1, v2, v3. I'll just write here capital D. Same way we'll be having Q2, which will be equal to pi by 4 d2 square into v2. Then Q3 will be equal to pi by 4 d3 square into v3. I'll just write this equation making v as the head of the equation. Firstly, here I'm having the lengths of the pipes, which are L1, L2 and L3. First of all, let's just write the Darcy-Weisbach equation, which is 4FL1 V1 square upon 2G D1. It is equal to 4FL2 V2 square upon 2G D2. The coefficient of friction is same for all the 3 pipes. That's why I'm writing it as F. 4FL3 V3 square upon 2G D3. Now as you can see here, 4F 2G will get cancelled as it is same everywhere. Then as I said, we'll make V as the head of the equation. Q1 is equal to pi by 4 d1 square V1. We can write that as V1 is equal to Q1 upon pi by 4 d1 square. Here I'll just write it for all of these three. V1 is equal to Q1 upon pi by 4 d1 square. 4 will go up, so it will be 4Q1 upon pi d1 square. Here we'll just write this, and the whole square will come divided by d1. Here I'll be considering 4f and 2g because the equation that we got, L1 V1 square upon D1 is equal to L2 V2 square upon D2 is equal to L3 V3 square upon D3. That is one equation. And right now what we are doing is to derive the equivalent length of the pipe. That's why we'll just take this 4F L2 into, instead of V2 it will be 4Q2 upon pi D2 square whole square upon 2G D2 is equal to 4F L3 into 4Q3 upon pi d3 square whole square divided by 2g d3. Now we'll be solving each one separately, which is h is equal to, this will become 64 because 4 square is 16 and 16 into 4 is 64. I have just opened the bracket. 64 f L1 Q1 square upon this d1 square whole square, so it is d1 raised to 4 into d1, which is d1 raised to 5. So denominator will be 2g pi square d1 raised to 5. Same way here, 64 f L2 Q2 square upon 2g pi square d2 raised to 5. Firstly we'll write this and then we'll make it separate. 64 f L3 Q3 square upon 2g pi square d3 raised to 5. Now writing all of these separately, which is comparing each one with h. The first one, second one and the third one. H is equal to 64 f L1 Q1 square upon 2g pi square d1 raised to 5. But here we'll make Q1 as the head of the equation. This will get multiplied here, so it will be 2g pi square d1 raised to 5 into h divided by 64 FL1, and the square root of this will come because here we are having Q1 square, so this will be the root of. Then same way for the second one, which is Q2 equal to under root of pi square d2 raised to 5 2gh upon 64 FL2. And then Q3 equal to under root of pi square d3 raised to 5 2gh upon 64 FL3. Then we'll write the equation for the discharge for equivalent pipe, and that will be equal to Q is equal to under root of pi square d raised to 5 2gh upon 64 FL. As for the equivalent pipe, the diameter, the length and the head loss, we have denoted it using L, D and H. Now we know Q is equal to Q1 plus Q2 plus Q3. Here we'll be substituting all of these values, which is pi square d raised to 5 2gh upon 64 fl raised to 1 by 2 is equal to pi square d1 raised to 5 2gh upon 64 fl1 raised to 1 by 2 plus pi square d2 raised to 5 2gh upon 64 fl2 raised to 1 by 2 plus pi square d3 raised to 5 2gh upon 64 fl3 raised to 1 by 2. Here one thing you will be seeing is pi square 2gh upon 64f is common everywhere. We'll just cut this and now we'll be left with d raised to 5 upon l raised to 1 by 2 is equal to d1 raised to 5 upon l raised to 1 by 2 plus d2 raised to 5 upon l2 raised to 1 by 2 plus d3 raised to 5 upon l3 raised to 1 by 2. This is how we can find the length of the equivalent pipe in the case of parallel pipes. And same equation we saw for the pipes in series. Again, I'll just remind you that equation. That equation was L upon d raised to 5 is equal to L1 upon d1 raised to 5 plus L2 upon d2 raised to 5 plus L3 upon d3 raised to 5. And this equation is known as the Dupuit's equation. And in today's video, we saw how we can derive the equation for the equivalent pipe in case of the parallel pipes. Thank you.